All right, time for one more little legalistic video about a really specific rule and or definition, and that is continuity. Or continuity just means, is the thing continuous? Is the function continuous, right? And a continuous function, sort of the way to think of a continuous function, is one where you could draw along the function and basically trace it without your pencil ever leaving the paper. So a normal line, it's easy to see it's continuous because no matter where you go on this line, your pen never has to leave the paper. Same thing with a parabola or something. It shoots off to infinity both directions, and there's no missing points or weird steps, so you can just kind of trace it without ever having to pick up your pen off the paper. This one's a little bit different though, the one I have drawn here, because it's got this missing point, right? So if I wanted to go from here to here, first of all, I'd have to clear this empty dot. An empty dot is a missing point, so you can think of that as like a giant pothole or like a ravine in the middle of the road. Sure, the roads come pretty close together, but then there's that missing hole in the middle. You can't really drive over a hole, right? If it's like a big valley or something, big ravine. So that's basically a break in the line. And to make it worse, you got this point up here. So it's like, well gosh, if I wanted to trace this line, I'd have to go along down here, then jump up, hit it right there, then come back and return to my path. So all that jumping around is sort of a tip off that, hey, this thing was not continuous. Anytime you have a question as to whether it's continuous or not, it's probably not continuous. The one exception I can think of is absolute values or something, where you have sort of a V shape with a sharp corner. Turns out that is considered continuous. Later, in several chapters from now, we get in a differentiation. We'll find out that this V shape, because it has that sharp corner, it's not differentiable, but it is continuous because you can trace along the V, and your pencil can take a sharp corner, no big deal, and it's traceable without leaving the paper. Therefore, that is continuous. All right, so we just saw that if there's a missing point, that's definitely going to hurt continuity. So why is that? So the general idea is your pen would not have to leave the paper. But what if they don't give you that information? What if you sort of need to prove it, almost like a geometry proof? Well, we got two rules. One is that the left side limit and the right side limit have to match. So a lot of time what's going to happen is they'll ask you, hey, is the function continuous at x equals 2? Like in this case, 2 is the big deal, right? 2 is where we got this funky dot stuff happening. So if you wanted to know if the function was continuous, if there is a spot it's not going to be continuous at, it's probably 2, because everywhere else it's just a normal line. It's that one spot we're worried about, and that's the one we're going to have to satisfy these rules. So the question is, do the left side and right side limits have to match? So do they match up? And in this case, they do. And you may recognize that if you watch the previous videos in this chapter. You realize that when those two do line up, that means the limit exists. So if you're ever looking for continuity rules in your book, what it'll probably say is that rule number 1 will be that the limit exists. But if you've watched the other videos, you know that the limit existing just means the left and the right limits match up. Unless something crazy happens and something shooting off to infinity. But usually for these continuous ones, it's like the nitpicky thing. Do they meet up? In this case, yes they do, because they both appear headed for the same spot. And then rule number 2 is the function has to exist. And it does, right? Because at x equals 2, sure, this empty dot means the function isn't right there. But there is a dot up here making up for it. So all real numbers are represented. If you plug in 2, you'll just get this number up here, 5, instead of what you thought it would be, 3. But the point is, the function does exist, but the function has to equal the same number as the limit. So what's going on is that these two lines, they're headed for the same spot, which is great, except when they get there, there's going to be a hole in the road because the dot's up there that should have been right there. It's like they just displaced that one dot that should have been here. They jumped up to here for no reason. But that means that because that dot is not sitting where it should be, right at the collision of the two pieces of the function, this is not a continuous function. So just like we figured out, hey, if I try to trace it, I would have to jump my pencil up to clear that gap. Same thing happens here because the f of 2 does not equal the limit. So in this case, f of 2, which is 5, does not equal the limit of f as x approaches 2. So basically when we plug in 2, we get something different than when we take the limit as x approaches 2. They're not equal, therefore not a continuous function. So that's a really mathy version. Depending on your teacher, depending on your class, this may never show up on the test. If you're in an AP class or harder college class, then you might be responsible for this in some little way. You just never know. But if you have an easy class or you don't think it's the hardest class ever, it's not AP, then yeah, maybe your teacher will let this one slide. All right, let's take a look at this one in like the non-mathy sense. We just want to know, is it continuous at x equals 1? All right, so x equals 1, that's where all this open and closed dot funkiness is happening. And doesn't look like it's continuous, right? Pretty obvious that it just takes a big old jag, so this one's not even a question, it's discontinuous. At 1. But what about at x equals 3? Because we're talking about continuity in general, and they'll usually ask like at x equals this or x equals that. So this time they're asking, hey, is it continuous at x equals 3? Well, yeah, I guess so, because if you go to 3, in this section of the graph, there's nothing interesting happening. It's just a single line, so of course I could trace that section of the graph around x equals 3 without my pen leaving the paper. Therefore, yes, it is continuous. And this last thing, interval notation, you're probably pretty familiar with it by now. If you're not, you can search the site real quick for my interval notation video back in Algebra 2 or something. But the point is that if they say, what about on parenthesis negative infinity, positive infinity, what they're saying is it continuous for all real numbers? So basically, if we went all the way from negative infinity all the way to positive infinity along this road, is there ever a spot where it's going to be disjointed? Our pen's going to have to leave the paper. And sure there is, right? There's this point right here. So it's continuous on the interval negative infinity to, oops, didn't want that second parenthesis. This is continuous from negative infinity to 1. And it's continuous from 1 to infinity. But you'll notice I didn't use square brackets on the 1. I used curve brackets. So 1 is not here. The only point that's missing out of all real numbers is 1, and that's where it's discontinuous. So basically we're saying, hey, this function is continuous for all real numbers except 1 when we write it down like this. So again, that just depends on how mathy your class is and how hard it is, whether your teacher will make you do these continuity intervals and junk, or if you can just let it ride. All right, last one we'll look at. Very funky. I didn't even ask any specific questions about this, so you just want to sort of look at this and say to yourself, what's going on? So the first big, these things are always continuous except at the weird spots, right? And we have two weird spots. At x equals negative 3, we've got this weird kind of pointy elbow thing happening, this corner. And then at x equals 2, we've got one of those displaced dot deals. So what's the deal? First, let's look at this point. It is continuous at that point because we could trace right past it without leaving the paper, and that's a closed dot, not an open dot. If it had been an open dot, and the point was up here, now we have a problem. But since this one was a closed dot in the corner, no big deal. You can just trace it right through with your pen, and that means that the limit exists and it's continuous. The function is continuous at x equals negative 3. Here, though, we have a problem because we got that open dot, closed dot above it kind of thing. So even though the limit exists at 2, because as we come across these two elbows, coming up this way and coming up this way towards 2, we're going to converge to that same point. It's coming to a corner, which is great. The problem is that the point we're converging to is not where the function is. The function is pulling a fast one, is right as we're about to get there, it jumps up to here for no reason, right? There's a random dot sitting up there above an open dot. But that's the way life is. That's the way math is, right? They give you tricky questions. So if you've got that dot sitting off somewhere else, this is not a continuous function. But if they ask, does the limit of f of x exist as x approaches 2, which is the thing we talked about in the previous video? Yeah, the limit exists because as you're driving up along these two roads, it looks like you're going to meet at the same spot, and therefore the limit exists. It turns out it doesn't matter that there's an open dot there. Because you think it's looking good right before you get there, it's looking like you're going to meet in the right spot, therefore the limit exists. And it's just that it's not continuous because that dot's missing. All right, so that is continuity. Pretty exciting stuff. Stick around for one more video, then we're going to be off to the wild world of analytical limits, which is like the crazy mathy functions version. Lots of algebra coming up, so stick around.